Hello. I hope you enjoyed your lunch. I hope not to bore you too much, and now you may feel a bit sleepy. So let me introduce myself. I am Ugarte. I work at Cisco Talos in the malware research team, mainly doing malware research. And before this, I did a PhD at the University of Deusto, so I come from the academic world. And when I was doing my PhD, I developed this framework, this tool named Deep Packet Inspector, which is a tool that allows to dynamically analyze samples, malware samples, that are protected by a packer. And it provides a result, a graph like this, that shows the different regions of the packer, how they are unpacked at runtime. It also shows several indicators, like its complexity, different features for different processes and different layers of the packer. And you might be wondering why I'm talking about the packet inspector if you came to a talk named PyREBox. So, well, it turns out that when I was developing packet inspector, I had to choose one among the many different options there are out there in order to do dynamic binary instrumentation. There are many frameworks based on different technologies. They have some advantages, disadvantages, they work in different ways. And of course, I had to choose one. And this brings me to PyREBox and why I developed yet another dynamic instrumentation framework. And I will explain you the motivation why I started developing this tool. And then I will go over the design principles. I will explain you how the architecture of this tool, how it is designed. I will show you some features, what you can do with PyREBox, what it can do for you. And finally, I will also show Malware Monitor, that's a set of scripts for doing malware analysis that I'm releasing as open source today. So you have already access to them in the main GitHub repository. So when one needs to choose a framework like this for doing any kind of project that requires instrumentation, first considers the technical aspects. So is the framework, does it allow to trace one single process? Does it allow to trace several processes? Does it trace the whole system so that we can monitor also the kernel or even the interaction between processes? What type of events can we trace, like instruction execution, memory writes or reads? Can we trace operating system events? And what about transparency? In my case, for instance, I work on malware analysis, so I care that, for me, I'm concerned that the sample that I'm running will not detect the framework. Also, there are some practical aspects, like how easy is to use this framework? Which programming languages can I use in order to implement my scripts? And then there are other aspects, like how often is this framework updated? Does it have a big community that can help me? Does it have a good documentation? Is the project even alive? Because sometimes it happens that someone codes a framework, uploads it to GitHub, and then there are no more updates in months or even years. So that's also an aspect to consider. So in my case, for Packet Inspector, going back to this online service, it is based on full system emulation because it allows to instrument the whole system and to also observe the relationship between different processes. And it's also based on QEMU, which is an emulator. It also allows user mode emulation, but I based the approach on full system emulation. And this kind of systems simulate the CPU from a physical perspective. They emulate a memory, they emulate the devices. So all we have is a physical view of the system. This allows us to boot and fully emulate a modified operating system like Linux, Solaris, Windows. There are many operating systems supported. And it also has a feature that allows to emulate different guest architectures over different host architectures. This means that we can emulate an ARM operating system over an x86 operating system because it has a component, the tiny code generator, that it is designed as a just-in-time compiler that it will disassemble the ARM or MIPS or whatever snippet of assembly code. It will disassemble it, transform it into some intermediate language, and then this intermediate language gets compiled to the host architecture. It also allows to do some fairly transparent instrumentation, and of course, QEMU leaves some artifacts in memory, some devices that can be detectable, and some of them can be mitigated. But the important thing here is that the emulated memory is not modified at all. We can instrument the execution of a system, of a binary, of any instruction running on QEMU without touching the emulated memory. So there will be no footprint of the instrumentation framework in the process that we are analyzing. We don't need to introduce any agent in the system, or at least PyREBox is designed in such a way that it doesn't need any agent inside the system. But we do have an agent for automating certain tasks. We will see later what we can do with the agent. This agent obviously is optional. We don't need to install it into the guest VM in order to operate with PyREBox. It is also a full system because it allows to monitor all the processes running on a system and also all the interaction between these processes. And it allows to instrument and to inspect the kernel address space. Then the QEMU itself doesn't provide the instrumentation capability by itself. So there are some frameworks like Panda or Decaf that are built on top of QEMU in order to leverage this emulation system in order to perform the instrumentation. But these frameworks have some, in my opinion, inconveniences. It's that they require to code the plugins in C or C++, and while it is completely efficient, and I also code sometimes in C++, I sometimes just prefer Python because it's faster, it has great libraries, and I just need to get the job done quickly, and I don't really need to code the complicated C++ plugin for a framework like this. Also, some of these frameworks have super cool features like taint analysis or like record and replay in the case of Panda. But the problem of these features is that they sometimes require complex QEMU modifications. And this makes the project more difficult to maintain. So what is PyREBox? It's another dynamic instrumentation engine that it allows interactive analysis. This allows to inspect memory and register during runtime. It allows to run some built-in commands inside an IPython shell. And it also allows to load the scripts, Python scripts, that can listen to different events in the system. They can register callbacks and can listen to events like instruction execution, like memory reads or memory writes, like the execution of a specific operational codes. Whenever a process is created or removed, whenever a DLL is loaded or unloaded from a process, other system events like context change. And these scripts also allow to extend the shell, the interactive shell, with new commands that can be defined in the scripts. So I've talked a lot about full system emulation, but if you have played with QEMU in the past, you may know that it has an accelerator, a KVM component. It's a Linux kernel module that allows to leverage the hypervisor technology in order to accelerate the execution, because instead of translating every instruction, like I said before, to an intermediate language and then compiling it to the host system, it executes natively the instructions in an isolated environment. But what is the problem with this kind of approach? The problem is that first the target, this is the guest architecture, and the host architecture must be the same. We cannot execute an ARM operating system on an x86 processor with a KVM. And also the other problem is that it's dependent on the host operating system. So KVM won't run properly on Windows because it's a Linux kernel driver, at least not in a straightforward manner. Also, PyREBox won the volatility plugin contest, but interestingly, it is not a volatility plugin. What it does is to leverage volatility for memory introspection. We will see later how it does it and why it needs to do memory introspection. And it is free software. It's published under GPL. It was published like a few months ago, and it's available in GitHub. So let's jump into the design of the tool. So first, there are some design principles that I followed. First, I wanted the interaction and the scripts to be in Python, not in C or C++. But this has a trade-off. That is that Python has a high overhead compared to C or C++ that is compiled to native code. So this has an impact, and we will see later that I made certain decisions in order to mitigate this overhead and to try to make this trade-off a bit more better for the user. Then also I tried to keep instrumentation as simple as possible, because I tried to keep QEMU modifications minimal. This is I think there are like around 600 lines of code. I think I have it in the next slide. So QEMU only has 600 lines of code of modifications, and the rest of the framework it's decoupled from QEMU. This makes it easier to upgrade to newer QEMU versions, but the trade-off, again, is that it lacks some advanced features, at least for the moment, like taint analysis or record and replay. In some problems, you may need to use these features, but in others, if you don't need them, it's fine. This is the architecture of PyREBox. It has different modules sitting on top of QEMU, with a very little number of modifications. There is a C++ component and then a Python component that requires the Python runtime to be loaded into the same process. Python offers the interactive shell and a Python-based API that can be used by scripts that first get initialized by this Python environment. Then the script can register callbacks. The script is bound, and it will be able to receive callbacks from the system and to perform different introspection operations. So these operations will go through the API, the Python API, and the Python API will first ask the C++ component in order to serve the operation. The C++ component will translate the Python object into a native object in order to interact with QEMU, but then it will not call QEMU directly. It will go through another layer named the glue, which abstracts away the QEMU internal structures from the PyREBox internal structures, in such a way that if someday they release a new QEMU version or some modification for QEMU that changes some structures, we would theoretically only need to change the glue and everything would run again. Also, as I said, we see the system as a full CPU, as a raw CPU. So we are not aware of any operating system abstractions like processes, threads, handles. So we need virtual machine introspection techniques in order to understand these abstractions. From the CPU, from the memory, we need to go up in order to understand which process is running, because at every point we only see a sequence of instructions being executed on the CPU, and that's all. So BMI is implemented in two sides. A basic part is implemented in C++ in order to do the process inspection, and then the rest is done with volatility, as I said before. That is used from the Python core, and we expose the QEMU memory to volatility. Volatility is a memory forensics framework, but in this case, it allows us to inspect all the operating system structures, like processes running on the system, which libraries does the process load in memory, which handles does it hold, what objects do these handles refer to, like does this handle refer to a process, does this handle refer to a file. We can understand all these abstractions by using volatility. We support both Windows and Linux for 32 and 64 bits, and we can do a process enumeration, DLL or cert library in the case of Linux enumeration, symbol resolution. We can extract all the exported symbols for all these DLLs, and this allows also to deliver certain callbacks to the user. So for example, callbacks like when a process gets created or when a DLL gets loaded. Also, as I said before, Python can be sometimes prohibitively expensive, especially for very frequent events like instruction begin or memory read. This is not a problem of QEMU or PyREBox itself. It's because Python is slower than native code. And if we want to trace every single instruction running on a system in Python, it's prohibitively expensive, obviously. But what I did in order to try to mitigate this problem is to introduce the concept of triggers that are C or C++ small snippets of code that get compiled and loaded at runtime. So there are something like this snippet that will just receive the callback parameters and return a very simple value, a Boolean value, saying if the callback should be delivered or not to the Python handler. So if this is the normal callback, the normal callback flow, when we insert a trigger, this is a shared library that gets loaded in memory, and PyREBox will ask first this shared library whether the callback should be delivered or not to the script. And in this case, for example, if we can do simple checks that allow us to, these DLLs also can keep some state, so they are not stateless, they can be stateful. There are mechanisms in order to save data between each pair of callbacks. So we can have some simple decisions that let us decide whether the callback must be delivered to the script in Python or not. It's easy to compile and install. It compiles and runs properly in Linux. Also, I've tested it in Windows 10 using the Linux subsystem. It doesn't require any kernel driver, so it runs as a process. It's supported by Docker too, so it can be run on any platform that supports Docker Linux containers. Starting PyREBox is like starting any QEMU session. It accepts options via command line in order to configure the devices. You can check the QEMU docs for this. There are some documentation on the internet. I also provide some example scripts on how to start a QEMU session, so it should not be too difficult to start using it. It also has a configuration file that allows to specify which scripts get loaded at the startup and some other parameters like the specific version of Windows or Linux that is being emulated in the guest, and some parameters related to the agent if it gets loaded in memory. The full documentation is here. It's hosted in this URL, so you can check it and everything should be documented. If not, you can open an issue in GitHub and I will try to document it better. And PyREBox, as I said, has an interactive component, which is an IPython shell, which is based on the QEMU monitor. So QEMU monitor is a shell exposed by QEMU in order to manage devices, to load or to save snapshots. And I added a new command, which is sh, that will jump into the PyREBox shell. The PyREBox shell freezes the system and allows us to inspect the memory and to inspect the registers. It also implements several built-in commands. It allows us to run volatility commands too, and to run the custom commands if there are any custom commands declared in the scripts. We will see later how we can declare a custom command in a script. It allows also to run Python snippets of code because it's an IPython-based shell, and it has all its cool features like autocompletion, syntax highlighting, etc. So let me show you a demo now. I hope the resolution is fine. Yeah, it should be fine. Okay, so here I have a PyREBox already compiled, and as I said, there are some scripts that I provide in order to start the QEMU session. This script just starts QEMU with certain parameters like the amount of RAM memory and stuff like that. It's also on the GitHub repository. We specify the image we want to boot and the snapshot we want to load. So we can load a snapshot with, I name it no agent because it doesn't have the agent. It starts a new screen for our VM, that is an XP VM, and there we have. Okay, so in order to see what we can do, let's start the process, and then we can go back to the cell. And here we are in the QEMU monitor. The QEMU monitor, as I said, is the typical QEMU shell that allows us to, for example, manage devices like the USB add, I think, yeah, USB add, USB del. It has many commands. It allows to save snapshots or to load snapshots. And then it has, as I said, the sh command that jumps into the PyREBox shell. There in the bottom, we can see the prompt that it has changed. And now the system is freezed. Now we can run any of the built-in commands. that we can list with this built-in command. And here, let me scroll a bit. Here. We have introspection commands that make use of the different BMI features, like listing processes, listing DLLs, listing symbols for these DLLs, CPU and memory manipulation commands like reading or writing register, reading or writing memory in different ways. Disassembly commands in order to dump assembly snippets from a given address in memory. Also, we have the capacity to set breakpoints in memory, both memory execution, memory read, or memory write breakpoints. And we have also some search capabilities like strings or regex searching. So let's start by first instance running the ps command in order to get the process listing. And now the BMI component has retrieved the list of processes from the memory of the emulated system, and we have a listing of the process. We can see that there is the calc that I started. We can list its DLLs. We can use the process name or part of its name. And here we have all the DLLs it has loaded so far. We can list symbols. For example, let's try to search for a symbol with this keyword. It also allows wildcards and for searching symbols. It takes less than 1 minute probably to update the symbols because it has to traverse all the processes in memory, retrieve all the DLLs, parse all the export tables, so it takes just a bit. And once it is loaded, the symbols are cast, so we can, in the following executions, it will just run immediately. Here it gives us the offset in kernel 32 of this symbol, of the symbol exit process. We can also set breakpoints, but since we don't modify, this is not like a traditional breakpoint in which we change the memory of the process and we put in interruption. We just have to trace the memory, so we are continuously executing the instructions, and we can tell the translator to notify us whenever it executes an instruction in a given memory address range. So we are free to set a breakpoint on one single address or the whole system address, the whole address space. We can put a breakpoint from address 0 to FFFFF. There's no limitation on that. So we can put, for example, if we go back to the list of modules, we can put a breakpoint on this base address and the full size of the cal.exe module. So we can do like this. And what happens? It tells us that we need to specify a virtual address space. This is because we are seeing the system from a full system perspective. We are seeing it from a physical perspective. So if we specify a virtual address, we need to specify which process does this virtual address belong to. So we need to use the proc command to set the process context of the cell. So all the commands that follow this will refer to the calculator, to the address space of the calculator. Now we can set the breakpoint. We exit the cell with C or continue or quit. There are several commands for exiting the cell. And in the very moment that we exit the cell, we enter it again. Why? Because the operating system started running, the scheduler gave some CPU time to the calculator, and immediately we stopped in the first instruction that executed in this process. So here we can use, for example, the this command in order to get, well, because of the resolution, the disassembly listing is not very good, but you can see that we can disassemble the instructions at the current instruction pointer. And then we have, apart from the built-in commands, all we have seen so far are built-in commands. We have also Python objects in this IPython cell. For instance, the CPU is a Python object. And given that we are in a Python cell, we have auto-completion features that, for example, let us inspect all the members of the CPU. This will change, for instance, for a 64-bit CPU in which the register will be RAX, RBX. It's all done dynamically. So we can use this as a Python expression. This is an int, a Python int. So we can just write, this is EBX. We treat it as a Python int. And there we have, you can write Python code there. Also, the API is a Python object because the API is a module. Modules in Python are also objects. So we have here all the functions. We can get also help for these functions. And we get the help for how to use the function. So we can inspect the system not only by using built-in commands, but also by using the CPU object and the API, the Python API that is exposed by PyREBox. So let's do something more complicated, like let's dump the stack by using some Python snippet. So we could start by creating a for loop and going from cpu.esp to, let's dump 0x20, and we do it every 4 bytes because we are in 32 bits, and then we can print like this the address, and maybe like this the content, yeah, then the address, and then we need to use an API in order to read the virtual memory. We can use the API, which is the API in order to read the virtual memory. We need to specify the process context. The process context is given by the CR3 register. It's the register used in order to differentiate the different address spaces for the processes in x86. We specify the address and the size we want to read. In each case, we want to read 4 bytes. And yeah, this will return us a string, a buffer. So we need to transform this buffer into a Python unsynced integer value. Okay, so we need a parenthesis here. Then struct.unpack returns a tuple, so it's the first value of the tuple. We close the parenthesis, and there it is. So we can write complex Python code in order to do memory operations. We can write registers, write memory, read memory. We can use volatility from this API. We can use basically any of the functions exposed by the API in order to interact with the system, to extract, to search memory for certain things, whatever you can imagine. But it's also possible to mix built-in commands with Python code. For instance, in order to do this, there is a command that dumps memory at a given address. For instance, we can do, I think, can do this. Yeah, this is the address where the calc process starts. So we can dump there. We see the MC header here. So dd is like a win-debug command. It allows to dump blocks of double words. But at some point, instead of using immediate expressions like this, integers, we can use a Python expression by using these curly braces. So we can specify cpu.esp. This will evaluate this Python expression, embed it into the built-in command, and we have the same result. Well, it has dumped a lot because I didn't specify how much I didn't limit the number of double words to dump, but in this case we see that the result is similar. Okay, we can list the breakpoints we have here. Because if we now exit the cell, we will hit a breakpoint for every single instruction that is executed. It will pop up a cell. If we disable this breakpoint or all the breakpoints, we continue, and we are again here in a running system. Okay. Scripting. So scripts can be loaded or unloaded or even reloaded. If we are playing with a script, we can modify it on the way and reload it. Either at the startup, when we start the QEMU environment with PyREBox, or by using a QEMU command or also a built-in command in the PyREBox cell. It also allows to start a cell at any time, so we can be tracing some events, and whenever certain conditions are met and that we want to inspect the system because we want to interact with the VM, we just use this function and a cell pops up, and we can start playing with the system. We, of course, can import and use any Python library, so this gives us the capacity to integrate PyREBox with any kind of binary analysis library that you may want to use or be used to. This is the initialized callbacks. This is the entry point of a script. Every script needs to declare this function, otherwise it will not work. And normally what you do here is to register some callbacks, because otherwise you will not have your script executed anymore. There's a class in the API named callback manager that allows to set up callbacks in an easier way. Here, for example, an example of how a callback is set, you just need to specify the callback type, in this case, process creation or process removal, the function that will receive the callback, and you can use a name in order to refer to the callback later in order to delete it or whatever. And that's all. Then you have a clean function that is called always when the module is unloaded, that must remove all the callbacks. But thanks to the callback manager, we just need to run clean on the callback manager, and it will remove all the active callbacks, and we don't need to care about removing one by one or anything. We can also specify requirements like this. This means that whenever a script with this requirement is loaded, the framework will first make sure that this other script is loaded in memory. So we can then import the plugins.getAgent and play with other plugins. So we can create different plugins that communicate with each other, that have dependencies on each other. Then one script is initialized. It is only executed when an installed callback is triggered, or when we define a command, a custom command. So we can create a function that starts by do underscore, and this will create a new command in the cell that gets loaded dynamically in the cell. So in the cell we can just write custom, it's like a keyword custom, and then the name of the command, and we run that function in the script. This is an example of two callbacks, like for process creation and process removal, the ones I showed you before. Each callback receives some arguments depending on the nature of the callback. In this case, it receives the process ID, the PGD, which is refers to the address space of the process, the CR3 register, and the name of the process. Also, there are some key concepts. As I said before, every process is identified by its address space. This has one particularity, because in Linux, when you traverse the list of processes, the list of tasks, you will see many tasks for one single address space, because there are many threads in the list of tasks. So when you list processes on a Linux guest system, you will see a listing of processes that have the same address space. For the moment, whenever we specify, for example, to trace all the instructions executed in a process, we refer to a process address space. So it will trace all the threads. In the future, we may implement thread separation. It should not be too difficult to add this capability to PyREBox. Also, each callback has its different behavior, obviously, because they trace different things. So you can check the documents. And then there is one more concept, that is monitored processes, because we can create some callbacks in which we don't specify, for instance, which process we want to trace. So we can set a callback on instruction execution, and we don't need to specify which process we want to monitor. But we can use the concept of monitored processes to limit the number of processes that produce whose events we listen to. So we can use these two commands from the cell, or using these functions from a script. Whenever we mark a process as monitored, all the events that we registered for one of these monitored processes, any of the processes in the list, we will get a callback. Then I also provide several scripts as examples in the GitHub repo, like for automatically running a binary and stopping right at the entry point, for monitoring memory writes and memory executions, for instance, quite typical for detecting unpacked code. Also, there are tests for every callback type and for the usage of triggers, so you can learn how to create callbacks and learn about the parameters, not only in the documentation, but also in the different examples that are available. As I said, there is also an agent. It is not needed at all for doing the tracing. It's only used for doing, at this moment, file transfer and automation execution. So an agent is a process running in the guest that it's listening in a loop, and from time to time it uses an invalid operational code in order to notify the host, hey, give me a command. Hey, do I have to do something? So whenever there is this invalid operational code, the translation engine will introduce a special callback to our host, to the routine in our host that deals with the agent, and this routine in the host will say, okay, I have a command for you, execute this for me. Then it will copy some data to a buffer memory that the guest agent has in the guest memory, copies some data there, and then the guest agent performs the operation that the host is asking for. This agent is working on Windows and Linux for both 32 and 64 bits, and it can be used either from the shell or from scripts by using these functions. And finally, I'm jumping into Malware Monitor. So Malware Monitor is a set of scripts that I am releasing today. Well, I actually committed them this morning into the GitHub repository. And it consists of 4 different modules for malware analysis. They are configurable via JSON file, and they allow to do API tracing. The API tracer module produces a text log and a binary log. The text log just gives us an impression of what the sample can be doing, and the binary log can be imported into IDA with a script that they also provide. We will see later how it works. And this module also can optionally extract the input and output parameters from every API call. For this, it leverages a database that must be generated. I provide you one for 32 bits, but you could generate also, I explain all the steps how to generate this database with all the API call information, which this database basically contains a listing of all the parameters that every API function accepts, their types, and it will dereference all the types. For instance, if an API accepts an struct as a parameter, a pointer to a structure, it will dereference the pointer, read the structure, dereference the pointers in this structure, and so on. Then the memory dumper module allows to automatically dump the memory of the process, the DLLs, let's say all the context of the process, and DLLs and allocated memory regions under certain conditions. So we can configure in the JSON file when we want to dump the memory. It's not a generic unpacker with some magic heuristics that, because I don't think there's any magic way to do it for every single packer. But as you will see, this framework overall gives us some useful information in order to determine the correct point to dump the memory. At least in many cases, we can understand by looking at the logs when we have to dump the memory. There's also a code coverage module that it produces an instruction trace. This instruction trace can be imported into IDA in order to colorize the different basic blocks so that we can get an idea of what gets executed, what not, in certain conditions, which path was taken, and a text log. And the particularity of the text log is that it doesn't record every single instruction, but only the transitions from one bad region to another bad region. What is a bad region? There's a tree for every process in the kernel that describes the memory layout of the process, and there is a node in this tree for every different memory region. So there will be nodes for each stack, for every heap, for every allocated memory region, not in any other way. There will be one node for every DLL, one node from the main executable code. So whenever there is a jump or a call or a transition between one bad and another, we create one line in this log. This is useful, for instance, in order to understand many packers that unpack some code in a buffer in memory that they allocate and then jump into this buffer. Sometimes they go back to another buffer and they have like several layers, but this allows us to understand from which instruction in which region to which instruction in which region it is jumping. So if we know that it is jumping to a buffer and we know that it is jumping to a certain instruction, we already have the original entry point. We can start analyzing from there. Then we have the memory event logger, that is the fourth component, which is horizontal to the rest of modules also. It events several memory events. It traces several memory events like memory allocation or deallocation, like process creation. It also detects whenever a process opens a handle to a different process in order to manipulate it in some way. Remote memory writes, memory sharing via shared memory regions. Also file reading and writing, file mapping, and it also monitors whenever the memory permissions change from the moment when the memory was allocated. And it's quite useful in order to track injections, to track droppers, to track downloaders that are getting some content from the internet and writing it to disk. It outputs a condensed test-based report with, let's say, model that it creates with all this information, a behavioral model, and a log of events, all the events it has traced. So let's see a demo about malware monitor. First, we need to configure it. So we enable the module in this list. And now we run again the machine, but we run it with the agent loaded, so it will automate absolutely everything for us. So it has started monitoring for processes named sample.exe. It's loading the database with all the API function information. And it starts tracing. So once it starts tracing the binary that has been copied right now and loaded, it detects the entry point of the binary. For this, it uses the P file module in order to read the memory of the guest system when the binary is loaded in memory, and it retrieves the entry point. Here, it's updating the symbol list. It has to update it several times because it's continuously loading new DLLs. For every DLL, it needs to make sure that it retrieves the symbols. And here, we can see that there are many breakpoints set. It's saying adding breakpoint at NTDLL. This is interproc, or the memory monitor. The memory monitor relies on this set of functions at NTDLL level in order to do all its operations. It's updating symbols. Okay, so here we can see also another line. It's following service-host.exe. We will see later why it is following this process, but it's obviously because the memory monitor has detected that the original process, sample.exe, is interacting in some way with this process, with service host. Either it created this process or opened the handle to this process and then started doing some operations like injecting memory or doing something. Whenever there is something like that, it will follow all the chain of different processes. Also, it allows to trace cases when it shares memory or when it writes to a file, then this file is read from the other process. As I said, here it does the same. It detects the entry point. It hooks the second process also in order to run malware monitor on this second process. I think it's enough right now, so we can unload the module. Once we unload the module, it produces all the different logs for all the different modules that were enabled. Okay, so I didn't show you one thing. This was the configuration I used for malware monitor. I enabled two different modules, the API tracer and the interproc, which is the memory monitor. Interproc is the way we refer to the memory monitor in the scripts and the configuration. The coverage and the damper modules, in this case, are disabled. Then there is one section for every module. The interprop one just allows us to say which logs we want to be created and which logs we don't want to be created. Then we have the one for the API tracer. It has also options for each of the logs. And it also has exclusion and inclusion list. For instance, we don't want to trace maybe NTDLL because it produces a lot of noise. Okay, we can exclude this module. We want to include some particular API inside NTDLL. We can use this option because this overrides the exclusion list. So we can exclude APIs, we can exclude DLLs, we can exclude function calls that are originated from a given DLL. For example, we don't want to trace anything that comes from kernel 32. We can put here kernel 32. And this overrides. We can say, okay, discard all this except the ones I list in this include APIs parameter. Also, the API tracer has a light mode, which runs a bit faster. As you saw, it just took like 1-2 minutes, not more, for tracing 2 processes. But in light mode, it runs even faster because it doesn't need to inspect all the parameters from every API call. In this case, I run it in the heavy mode. So let's take a look at the logs. First, let's start with the basic stats. Basic stats is the summary of the memory monitor. So we have 2, one for every process ID. We start with the first one. We have some basic information about the process, not really important. The list of DLLs that it loaded with certain properties like the memory permissions, like the file it is mapped to, like the number of symbols, but we can jump to the interesting part. Here we have other BATs. This is other regions allocated in memory that do not overlap any of the DLLs or the main module. And here, this module allows us to monitor 4 different properties. The first one tells us if it is a stack, if it is a heap, or if it's neither of them. Then the second column tells us if the memory is private or not, if it can be shared with other processes or not. The third column is a volatility plugin that has an heuristic in order to detect memory injections, the malfind plugin. So if the malfind plugin thinks or detects with its heuristics that it might be that this memory region might contain some injected memory, we will have an I here. And then the last one is the another flag that determines if the memory permissions were changed since the moment the region was allocated. So if we detect that the region permissions are changed, we mark this with an M. I think it was an M, yeah. And then we have another section for memory injections. Whenever you see a process create another process, since we trace at NTDLL level, you will also observe, for example, when a process uses the create process API, if you monitor the system at NTDLL level, you will see many of these injections. So it will inject to certain addresses. It's part of the process creation. But here, I can advance it. This is not typical. This line is not typical. First, because the origin of the memory copy, this is where the buffer that was copied is located. It's in the address space of the main module. And then this is a memory region that probably it has allocated dynamically. Then we can go to file operations. In this case, it doesn't do any file operations, the main process. And then the section maps. This is all the memory, all the files that it has mapped in memory. As we can see, here we also see service host as an artifact of the fact that it created this process. We can jump to the other report for the service host that was created by the original process. We see also some basic information. And then as well, we have all the information about the different DLLs that it has loaded. And let's go to the interesting part. Here we have the memory region that we saw an injection in the first log at 90,000 X. And this one, it has page execute and read-write permissions, typical in unpacked buffers. And it has also the injection heuristic by the malfind volatility plugin. If we go down, we also see here that it is writing to a file, to gore.exe. So this, for instance, could already be some kind of persistence technique or way of the malware in order to write to disk a file in order to ensure persistence. This is just a guess. Obviously, we are starting the analysis, but it's already giving us some information. And let's go to the function calls. Okay. Here, we can do, for instance, some very quick check. Let's check for the file name. There we have it. It has traced this API, set file attributes. It shows us the input and output parameters, just like any API tracer. And we have also a copy file, a create file. So, and here also we can see the origin where this call was done. It's this buffer, this injected memory buffer. So, okay, we don't know if this is the final stage of the malware, but we know that there is something there that is worth being analyzed. We can decide to dump the memory at that point. So we can, for example, try to see if this is a common call, if this is happening many times in the trace. Okay, this is the first and the last call to create file A. So this should be a good moment to dump the memory. When the process executes this API, should be a good moment to dump the memory. So if we can go back, configure the JSON file, we go to the dumper, and here, instead of null, we say to dump at this API call. We activate the rest of the modules. I can also activate the coverage one. And we run it again. There it is. This will take just a little longer, maybe a couple of minutes. So I will jump directly into the following VM where I already have the results from this run so that we can save a couple of minutes. Okay, so here we have IDA, and the dump looks like this. Let me show you. The dumper will produce something like this. This is the main executable. Then it has a number of modules loaded on different addresses. This corresponds to the different DLLs it has loaded. And then we have a number of regions of code or regions of memory that were dumped that are not associated to any of these DLLs or the main process. So in order to start the analysis in IDA, we import the main executable. And then, as we know that the memory region in which we have some interest was loaded outside the main binary, we can load an additional binary file. We know it was here at the 90,000. We just specify the correct offset. There it is. And it loads this module. So we can see that IDA has already identified a lot of functions. And here that we have the entry point of service host, we see that the entry point of service host was probably hooked because it's pushing this into the stack and then doing a return, so it's jumping into the entry point of this new buffer. Okay. We can import now the different information that we extracted from our malware monitor run. So we can run one of the volatility or one of the IDA scripts. We have two. the one to import the coverage information and the one to import the function information, the function call information. So we can use this script. We go to here, we have the binary file for the coverage, and it paints some basic blocks. Well, in this function, everything has been executed, but we will soon find one in which not every code path has been executed. For instance, here. Here we can observe which code paths have been executed and which haven't. That's something also useful during the analysis. This, as we can see, has already dumped the results. So now we would proceed the same way. We unload the module, it will generate the logs. And then we have another script that it should be here. This script allows to import the information from the function calls. It creates this new tab. It allows to load the function calls. And it loads the function, as we will see, it allows to load the function calls from the two processes. So we need to select the correct process ID for the process that we are actually inspecting, that is service host with injected module. And here we can see all the information about the API calls. We have different filters, like we can see the create file API that we had before. We can search for other functions typical in malware, like creating mutexes, whatever. And then here, we can also go to the caller, because we have information about where this function was called. Yep. And here we can see that the function was called from this address. We have also one more feature here, that is to apply. This updates also colorizes IDA. As you can see now, it's in a darker color. So it will mark with this color every location where an API call was originated. And here we can do right-click and also show the information of the API calls. This case is particular because it's showing a lot of different functions, because this malware uses this function as a kind of dispatcher for API calls. So every API call is originating from here. But in other cases, in which the API calls are obfuscated because the addresses are loaded at runtime, you can automatically look at the right-click somewhere, go to the context menu and see which API calls it was calling there, see all the parameters. If API function is run several times from the same point, you can see all the different parameters on every single call that was made. So for example, it is run on a loop, you can check all the parameters every time it was called inside the loop. Okay, can I quit this? And that's it. Malware Monitor is a tool that can help in the first stage of malware analysis. It gives us some overall information, like how it is bootstrapping its main payload in memory. It gives us some information about how to unpack it, some hints that can help us in the first stage of the analysis, and it also provides us some information that we can import into IDA in order to enrich the ADB and to make analysis easier. What's next in PyREBox? Well, we have on the roadmap adding support for other architectures like ARM or MIPS, maybe other operating systems. It would also be interesting to have it as a debugging backend of IDA or Radar. It's also an idea that we thought about in the past. And maybe integrating PyREBox with other binary analysis tools. Since it has all the Python scripting engine, it should be quite easy to integrate any Python tool into the framework. And also, why not, given that the PyREBox is designed in such a way that it only requires a minimal number of modifications in QEMU, we can always put PyREBox on top of other QEMU-based frameworks like Panda, for example, and maybe take advantage of some of the advanced features it has, like temporal analysis or record and replay. So thanks for listening, and if you have any questions, I think we are running a bit out of time, so we can catch up later or as you wish.